of personal significance to me because this is one of the coolest events that I have ever missed. I saw the eclipse, but if you missed it, there's a tiny dot right here that happened at around 11 p.m. This was an asteroid that impacted the moon during the lunar eclipse, first of its kind ever observed. About 100 telescopes across the planet observed it. I was watching the eclipse with my friend. I was going to eat a cookie at the time. My friend was watching. My friend saw it. I missed it. It haunted me for the rest of my life. Anyway, this was caused by a rock. You see this beautiful artist's impression of the rock. It was about 30 centimeters across, traveling at around 61,000 kilometers an hour, so fast. And it blew a crater about 10 to 15 meters across on the moon, releasing about 1,500 kilograms of TNT. So, like, millions of birthday cakes, basically, equivalent. This was a huge explosion. And it triggered a light that was bright enough to see on the moon, 380,000 kilometers away. But this is not that impressive in terms of impactors in space. Anyone know what the bad day for the dinosaurs was? Yeah, this one happened a little while back. This was so disruptive to our planet's history 65 million years ago that it left traces in the rocks all across the planet. It literally calcified the rocks of our planet, and then those were buried underneath new normal rocks. But if you really dig deep, you can see all around the world, the moment that this happened, 65 million years ago, there was an asteroid 10 to 15 kilometers across, slammed into the Earth at 22 times the speed of sound, blew everything up. The dinosaurs died that day. It was very sad, and it released the energy of about 100 trillion tons of TNT. So we're talking quadrillions of my birthday cakes now. This was a planet-altering event. It changed the life of Earth today by over a second. Like, this thing hit the Earth like a merry-go-round, like a drunk kid hitting a merry-go-round, and it changed the rotation of the merry-go-round. This was a planet-altering event. But believe it or not, this was not actually that impressive in terms of the entire scope of Earth's history. The Earth is orbiting a fairly powerful thing that you may have heard of called the Sun, which is about 1 million times more voluminous than the Earth. And it occasionally shoots out these giant blasts called solar flares, and I'm going to grab my extremely accurate looking sun over here. This is the sun, guys. The sun is made of plasma, which is basically what happens. You take a solid, you heat it up, you get a liquid, you heat that up. You heat that up even more, the atoms melt or like dissolve into individual subatomic particles. And that means you have positively charged protons and you have negatively charged electrons, and they're just floating around. So plasma is magnetic, which is why you've ever seen those like plasma ball toys. You can touch them and they make these cool arcs, and you feel like Emperor Palpatine. And it's great. But the sun is made of that, so the sun is a very magnetic ball. Now, the sun is also turning. It turns about once every 28 days, and if you know some stuff about electromagnetism, you know that if you spin a charged thing, it generates a magnetic field. So the sun is magnetic, but the sun also generates a magnetic field, so the sun But it, it knots itself up, the magnetic field, and then all of a sudden, sometimes these knots undo themselves very violently. And when magnetic field lines untie themselves and the sun is magnetic, it pulls huge strings of itself and launches them into space at nearly the speed of light. So insanely powerful events just shooting into space. There's the Earth for scale, by the way. These things are huge. And there was an event in 1859, September 1st to 2nd, called the Carrington event, which was a giant solar flare that shot a bunch of radiation and protons and high energy stuff at the Earth. And it was illustrated. There were aurora visible almost during the day. It was so powerful. All these power lines, cables, and stuff that was like very preliminary electric stuff going on at the time, 1859. Everything caught fire. It was a bad day. And what I find even funnier about this is that September 2nd was a Friday. So just picture you and your guys, like, you're hanging out, you've just finished your, like, legislative job or something, and you're like, hey, boys, want to go to the pub? And so you, like, text, or I guess you telegraph your boys. You're like, hey, I want to go to the pub, where actually it sounds like beep, 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 or something. And then they're like, okay, so we'll go to the pub. You taking your horse? I'll take my horse to the pub. Wait, we need a designated horse rider if we're getting drunk. And then you go to the pub, and suddenly, bang! Your power lines, the pub's on fire, everything's on fire, and it's terrible. And that was caused by something 150 million kilometers away. So yeah, big boom. This is 100 million trillion tons of TNT equivalent. This is so many birthday cakes, it's not even worth mentioning anymore. So yeah, the sun causes some pretty big explosions. It's not that impressive, though, compared to something that happened to the Earth about 4.5 billion years ago. But you look at the moon, I like the moon. We owe the moon's existence to a Mars-sized planet that slammed into the Earth 4.5 billion years ago. Why do we know this happens? Because when Apollo astronauts went to the moon, and they picked up some moon rocks, and they sailed back to the Earth, they landed on the Earth, and the NASA scientists are like, hey, give us the moon rocks. You give us the moon rocks, then you pick the moon rocks, chemical study of the moon rocks, and then you study the Earth rocks, study the Earth rocks. If you take out the soil and the bacteria and all stuff that makes Earth rock Earth, it's literally the same chemical composition. The moon is made of the same regolith as the Earth, which means they are kind of chemical cousins when you take the samples. And that led to the prevailing theory that the Earth and the moon were formed from the same object, which more precisely was a giant explosion that happened between two planets 4.5 billion years ago. So this planet was moving at like 20 or 30 kilometers a second, and these planets just slam into each other. And when you're talking about collisions of entire planets, it's not like bowling balls bouncing off each other. It is like jello sloshing through, and everything just explodes. So this was about 10 or 100 billion trillion tons of TNT, which is big. Like, we're talking Death Star, Alderaan type stuff. So it's a very large explosion, but I think we need to skip a few orders of magnitude if I'm going to finish the talk on time. So the next thing I want to talk about is giant stars near the end of their lives, huge, giant red stars called red giant stars that are orbiting these very small but very attractive companions. And I mean attractive in like gravitational sense. They're very dense, so they have a lot of pull, and they're like hoisting matter off of this red giant. The red giant is just sort of orbiting. Okay, picture this. There's a red giant star, thousands of times the size of the sun, orbiting around this tiny thing the size of Earth. That is a huge size difference. That's like the difference between this circle and like an ant. And the ant is tossing this huge circle around in a big orbit and is siphoning gas off of it. And that gas is spiraling down onto this tiny little white dwarf star. Now, white dwarf stars are really dense. Like a white dwarf the size of Earth weighs about as much as the sun. But they have a limit to how dense they can get. And if you put more and more matter onto a white dwarf, it gets denser and denser until it reaches a point called the Chandrasekhar limit, which is about 1.5 times as much as the sun. So as soon as 1.5 suns worth of matter falls onto this white dwarf, it will have no more. It's like a baby you keep feeding until the baby pukes. And when this white dwarf star explodes, it really explodes. It explodes with a power of about 10 billion trillion tons of TNT, and this is like as far as I'm going to go with the TNT analogy because it's just stopped meaning anything. But it has the power to light up an entire galaxy. You see, there's the galaxy before, there's the galaxy after the Type 1a supernova has happened, and this is millions of light years away, like across the universe. But the interesting thing about Type 1a supernova explosions is that because they all happen at the same point, 1.44 times the mass of the sun, they all blow up with the exact same brightness, which means that if you see one that's dimmer than another one, you know that the dimmer one must be further away. It's like a standard metric of brightness. And that is how we measure the distance of distant galaxies, by looking for these explosions, because you know how bright the explosion is supposed to be. So if you look at how bright it appears, you can sort of translate how far away it is. Yeah, it's like if all babies vomit the same amount of vomit, then if the baby's further away and you see less vomit, you know that smaller baby, the baby's literally further away. That's the best analogy I can give you. So they're called standard candles, and compared to some other explosions, they're pretty weak. So let's go on to the next one. There's cooler supernova explosions. The conventional kind of supernova explosion, a core collapse supernova. So a giant star, like a red supergiant star, 10,000 times bigger than the sun, maybe. At the end of its life, will collapse in on itself and form a supernova. This is because giant stars have layers, like onions or people, and they start by burning hydrogen, and they cook the hydrogen, and then they start fusing helium, and then they start fusing carbon, on and on and on until they get to iron. And you cannot fuse iron because iron is dead weight; it doesn't fuse. But to simulate this exactly, I need 2 volunteers who are willing to crash into each other. Do we have anyone brave in the audience? Is that an end? We have another hand, and you. Okay, I'll take you two. You raise your hands first. Come on up. You are going to be the outer layer of star, and I'm going to be the core of the star. If you don't mind. Okay, so I need to preface first. There is a gym at UBC. I did not go to it. So I don't know if my arms can handle this. But I want you to lean against my hands and put all your weight against it. Okay. You might do it facing forward so you don't just instantly fall. I got it straight. Okay. Sounds good. Want to lean? Okay. So I am the core of the star. I am the radiation pressure. I am the hydrogen that's fusing and pushing outward. I'm the core. These people beside me is the gravitational pull of the star pulling inward, just like you are all pulled to the center of the Earth. The star has gravity too. I'm fusing hydrogen. I'm burning hydrogen. Suddenly I'm out of hydrogen. Oh, I'm going to start burning helium now. Burning helium, burning helium, burning helium. Oh, I'm out of helium. I'm going to burn carbon now. Carbon, carbon. I'm out of carbon. Now nitrogen, nitrogen, oxygen. I'm going to burn neon. I'm out of neon now. I'm going to burn chlorine, phosphorus, silicone. Uh-oh, I'm burning iron. I'm running out of fuel. And in collapses the star. In on its Thank you, volunteers. So it's like 2 symbols, like in the band, 2 symbols crashing into each other, except these symbols weigh about as much as 10 times as much as the sun, and are smashing into each other at about a quarter of the speed of light. So when this happens, it releases about 1,000 times more energy than a type 1a supernova. It has the power to light up an entire galaxy. In fact, one of these things that people saw on Earth in the year 1054, it's documented by Chinese and Japanese scholars, was visible in the sky during the daytime for 23 days. Like when the sun is up, I mean. At a distance of 6,500 light years away, this is like an appreciable fraction of the galaxy distance. So these things are very, very powerful. And when they collapse, they can form either a black hole or a neutron star, which is a tiny, tiny ball of neutrons. And when you get neutron stars, you can get stuff that's even more powerful. So picture 2 stars that have gone supernova. And they've all made neutron stars, these tiny, compact, glowing balls of neutrons. And then these neutron stars spiral in and crash into each other. So that's like fusing Pokemon at that point. Like the original supernova was like upgrade this Pokemon to a powerful Pokemon. So it was fused them together. That's going to be insanely powerful. And in fact, these things are so powerful, they literally send ripples in the fabric of space-time. There's this observatory called the LIGO Observatory, the Laser Interferometer Gravitational Observatory. It's a very fancy name. It just basically means we're going to look to see how much space jiggles. Because literally, just like kind of sticking your finger in a pool will send out ripples in the pool. Spinning things around each other in space sends out gravitational ripples. And when these things smash into each other, they send out explosions as powerful as up to 50,000 type 1A supernova equivalent. So, like, I'm talking an entire solar system of birthday cakes. And they cause noticeable ripples in the fabric of space. And that was detectable. But let's keep going, because I think we are a little short on time. So let's keep going up to the next level. There are things called gamma ray bursts. When a star goes supernova, sometimes it collapses if the star is spinning. Like, if you go ice skating and you're spinning, and then you pull in your arms, you start spinning faster and faster and faster. Just like if you're underneath a pool and you spin some water, it's going to become a whirlpool, and it's going to like funnel the water downward. When a star is spinning and it collapses and it starts spinning faster and faster, it channels its plasma and gas into these beams. And when it collapses at full speed, a quarter of the speed of light, it shoots out these beams into space, these like gamma radiation beams, and it can puncture through an entire galaxy. These things can cook planets on the other edge of the Milky Way galaxy. It's terrifying. So to simulate this, I need 2 volunteers. No, I'm kidding. We're not going to. But you know what this is like. This is literally just a real-life equivalent to the Death Star. And there was one of these, the most powerful one ever observed, was given the very original name, I'm going to read this,